Hello, folks. Hello, folks. Can I get everybody's attention? We're going to start with the industry panel. And I want to start by saying this is the first year that we are doing such a thing as an industry panel. We had a visitation weekend last weekend, and some of these people were also on that panel last weekend. And I thought that it went very well. But I don't have a very concrete expectation of what's about to happen. so we'll just see. But we're very honored, as I said this morning, and as other people have told you this morning, Boulder, the department and the associated research institutes are really a hotbed of cutting-edge science. And that doesn't all happen in the university setting. And so we thought that a very important aspect of, going through, getting a PhD, one of the paths that you may take is in the private sector, either working for a company or being your own entrepreneur. And so it was pretty easy to come up with a long list of alumni from our program who have gone on to be luminaries in various industries. So I'm really just proud to have this panel of distinguished people here to talk to you. And let me introduce them. I'm just going to go in alphabetical order, and then we're going to pass the mic down and have each of them give a little bit of an introduction better than I could about sort of their background and story. So we have Ruth Bloom. Ruth, could you... Yeah, Ruth Bloom, who's the Vice President of Engineering at Integrated Dynamic Electron Solutions. We have Scott Davis, who's the co-founder and CEO at Vescent Photonics. We have Maya Fabricant, who's a research scientist at Quantinuum. We have Jen Gannon, who is the VP of Research and Development at Computational Physics Incorporated. We have Daisy Raymondson, who is the CEO of KM Labs. And we have Chris Wood, who's the VP of Photonic Technologies at Cold Quanta. And there's going to be one more panelist who got hung up and who's going to come in the middle, and that's Chris Myatt, who's the founder and CEO of LightDeck Diagnostics. So maybe, if you wouldn't mind, maybe we could start at this end, and you could introduce yourself and tell us a little bit about, for lack of a better word, your story or your background, and maybe a little bit about your company.
Okay. Let's see, testing. Well, I love CU. I love Boulder, and I've been fortunate enough to work here for 30 years now. The brief version of my story is, without going into all the companies, I've worked in 8 different business models now, from the CU to government lab at NIST to venture capital funded firms to private family held firms to a small SBIR house to Lockheed Martin, big aerospace. Started my own company a bit and worked with Chris Myatt here, who's not here yet, at one of his companies, and have done LiDAR recently, and now I'm at Cold Quanta, back with Dana Anderson. My story, Dana was a professor of mine also. I took graduate laser physics from him, probably in, I'm guessing, 91 or 92. And his lab was right across the hall from mine. So that's my connection to Dana. So I've come full circle back to the, kinds of lasers we were using back in 1989 when the first magneto-optic traps, and we were both building our own lasers to do all that at Gila. So it's fun. I've been, like I say, in industry, I've been able to build lasers of varying types, almost every type, for 30 years, I'd say. How's that?
Yeah, that's great. And could you just tell us just maybe the 2-minute version of Cold Quanta, what Cold Quanta is?
Yeah. Cold Quanta is a quantum company in the new verbiage for what that means, but in Cold Quanta's case, it means that we're building a quantum computer. Everybody who says is doing quantum is building a quantum computer. But in our case, we also build picks and shovels, and what that means is we build the glass cells that make the magneto-optic traps, that make the double mots, where you have two traps that make the Bose condensates. We build those. We have 10 years of technology where these glass cells are now monolithically integrated, and the traps are all built inside them, and the optics for the magneto-optic trap are in a little compartment all surrounding the cell, so it's come a long ways there. The Cold Quanta has a division called the Quantum Computing Division, which we call the Quantum Computer Hilbert. We have another kind of pillar or division in the company that does what's called quantum emulation or simulation, and that's where we have a Bose-Einstein condensate that can be programmed from the cloud. So users in the cloud can actually pay for a service and do experiments on a Bose-Einstein condensate that's housed over there in East Boulder. And you design the experiments from the cloud, and we run them. We also have a whole product line of quantum sensors, RF sensors, and atomic clocks. So there's a lot going on at Cold Quanta.
Thanks. Jen.
So, hi, everybody. So I came out to CU in I think 1999, and I was told I would never leave Boulder, and I laughed because that was not going to be my path. I was definitely graduating, and I was definitely going to NASA. And that didn't happen. 25 years later or so, here I am still. After I left CU, I was a federal research scientist for over a decade. Loved that, worked at USGS and NOAA in the area out here. I'm probably a little different than the rest of the panel too, because I know absolutely nothing about AMO. So don't ask me any AMO questions, I won't be able to answer them. I do space weather, space physics, and I work mostly with, on NASA NSF grants doing basic research. I run our R&D division, which funds internal development of research and instrumentation for space weather. And I work a lot with our federal partners, still working with my friends and collaborators at the NOAA Space Weather Prediction Center. Yeah, so I guess after I left federal service, I decided to start a business, and they say fail fast, which I did. So 6 months later, I stopped that company, quit that, and joined CPI, and I've been there for 6 years, and I love the work I do there. I mean, it's a great combination of being able to do actual research in an industry environment and also be able to sell things with a commercial application. So it's research with a practical bent to it. So CPI, I guess just to give kind of the 2-minute spiel, we do a lot of support for other government agencies as well. I'm also a little weird at CPI. Most of CPI are upper atmospheric physicists. They don't work with the power grid or with the radiation belts or space physics like I do. They support NASA missions, NASA Gold satellites. Some of the work at USNO, doing astrometrics, which is the coolest word in the face of the planet, I think. And so we have a big presence there in the DC area, and that's actually where CPI's main office is. And then we've got a small office out here in Lafayette where most of our commercial work actually happens.
Hi, I'm Ruth, and I graduated from CU in 2014. I studied AMO, which is sort of the generic thing to study here. But actually then I went on kind of wanting to do something a little bit more applied. At the time, there wasn't a big applied industry for AMO in Boulder. That certainly seems to have changed. And I actually went to work for Intel. And it did not take long to conclude that big companies weren't really for me. So I went and found like a little kind of SBIR type place. There was just a kind of a small spinoff at the Department of Energy labs in California, and that's where I still am today, even though the company's grown a lot. We make tools for transmission electron microscopes, which are these very, very large electron microscopes that people use to resolve structures of things at the atomic scale. If you've seen that really annoying picture of the coronavirus everywhere that's got like every atom resolved, that's how they measure that. We did not measure that, but that's what electron microscopes are for. But they're not very fast. And so what we sell are tools that allow them to take movies. And this is particularly useful to like materials scientists, and sometimes we shoot lasers into them too, which is kind of where my AMO background comes in. But anyway, it's very, even though it's a corporate job, it's very sciencey because we're basically kind of like that really awesome postdoc who built you this crazy apparatus like for hire by contract. And so we build a lot of scientific instrumentation for customers at universities, national labs, and stuff like that. And actually, my company's based in California, and I now work remotely at it. So I'm sort of also the I guess the representative of the year 2020 here. I think that remote work in Boulder is sort of a growing community, and it's kind of interesting to see how that's going to evolve over time. I'm not convinced it's going to go away as the pandemic winds down. It's actually been a really nice career path for me at any rate. But as years go on, we'll kind of see, I think, a lot more people seeking out beautiful places like this. And also, it's an interesting thing as well because it's very common with couples who are both technical that there's only one job that's available in a given town for them. And the two-body problem often really is a limiting factor in careers for people like that. And I think that remote work is also going to change a lot of those aspects, making careers more flexible too. So yeah, I think that the PhD in physics here, even though I've switched fields, was still, definitely is still incorporated into my job in terms of just like the culture of, really building your own instrumentation and stuff like that exists in AMO. I think it has a really universal value, and I think that kind of stuff also exists in other fields at CU too.
Hi, my name is Scott Davis. I'm one of the co-founders of Vescent. I'm now the CEO. I've been the CEO for 2 years now. Before that, I was thinking of going to physics grad school, like all of you. I was talking to Chris Wood. There were no panels. There was no feeding me dinner. I did actually come out to visit, and you hosted me, which is you took me to Old Chicago, and you told me about, I learned about beer from you. I've been learning from you, Chris, for many years. I decided to come. I knew I was going to come. I knew I was going to go to Jilla. I thought I was going to work on, I knew I was going to work on something in atomic and molecular. I met David Nesbitt, who's over there. He was my advisor. After I met him, I knew I was going to work on molecules. I had a tremendously fun time in graduate school. Then I thought I would be a researcher in National Lab. I did an NRC postdoc at NIST in Gaithersburg. I had a great time. I really miss Colorado. Came back, worked for a small company called Metal-Arc Optics, met Tom Bauer, who's the founder of that. He's still a friend. Tom is a great supporter of the community. He's been very successful. Then I started Vescent with two co-founders, another one also CU Physics out of Jilla as well. We actually started it to do a photonic integrated circuit play. I use electron microscopes to look at nanophotonics and structures. They are very, very cool. I was the CTO at the time. When you start a company and give yourself a fancy title, it's easy. Well, there was only 3 of us. We were all it was the C-suite, was the whole company. We got that technology to work. We figured out a way to bend light without any moving parts. The autonomous vehicle craze came along, and we had a LiDAR with no moving parts. We sold that technology off to Analog Devices, a big public company, in 2016. It was a life-changing event for me. We was, in the parlance of entrepreneurship, it was a very successful exit. We had a piece of the company that was doing what we called AMO then. Now it's called quantum. That's the new word for AMO. I found, if you want to get funding. Working at a big company wasn't a great fit for me. I came back in January 2020 as CEO just before the pandemic hit. My timing was perfect. Those were scary first quarter, but we did really well. We've tripled in the last 2 years. We tripled the size of the company. We're still small. We're only 41 people. But we manufacture, this time I am doing AMO and quantum. We manufacture tools. We're a picks and shovels company. One of the things I say is, we're mile high technology transfer. We transfer a lot of technology that comes out of places like NIST and JILA and other places, and we invent new technologies as well to take things that are normally only done in the lab, and we take them and let's get them on a ship. Let's get them out in an oil field. Let's get them, let's really sort of where the rubber meets the road. I say from Nobel Prize to the marketplace. And so things like optical frequency combs that won the Nobel Prize in 2005, Jan Hall here in JILA, he shared it with Ted Hench. Or things like Bose-Einstein condensation, which also won the Nobel Prize. I joke that I wouldn't be accepted to JILA nowadays. I got in before the Nobel Prizes. But I'm having a tremendous amount of fun. It all started with my education, my physics education at CU. I still collaborate with a lot of the folks that I met, people like on this panel. It's great to see some younger folks here as well. We're not all, I guess, Chris was saying I should have gray hair now. I should, I don't know why I don't. It's a tremendous community. There's a tremendous, people who get physics degree from CU, they get jobs. If you want jobs in industry, you are going to be sought after. We are certainly always looking to hire folks that graduate from there, both at undergrad, master's, and PhD level. And there's just a tremendous community of industries, big and small, all the way from Lockheed Martins to little teeny startups to biggish startups. And there's a great base of national labs and the university itself and the Joint Institute, like JILA, Joint Institute between the university, and places like GLASP. And it's a tremendous sort of, I don't know, high-minded community, I guess is maybe high-minded for high altitude. It's a fun place to be. All right. You have your own.
Says it's on. Yeah, there we go. Got to be 10% smarter than the machine. Okay, hi, I'm Maya. I'm definitely the most junior person here. I got my PhD in 2017, studying the M in AMO, and then I did a postdoc at Lawrence Berkeley Lab doing the O in AMO, and now I work for Quantinuum doing the A in AMO, and we are also a quantum computing company. Yeah, so we're based out of Broomfield. Our local branch is based out of Broomfield. Until recently, we were part of Honeywell, Honeywell Quantum, and then we spun off, and we have just merged with Cambridge Quantum Computing. So even though we have a local branch in Broomfield, we also have another experimental office in Golden Valley in Minnesota. We also have offices all over the world as part of Cambridge Quantum. And I do R&D for the quantum computer that we are building. So we are focused on the quantum CCD architecture, so we work on trapping ions in microfabricated traps. And so we have a commercial side and an R&D side. And so I'm basically just a research scientist for them and do sort of research a lot like what you might experience in grad school. And that's really fun for me. I thought maybe the only avenue to do that kind of research was academia, but it turns out that more and more you can do like pretty fundamental research in industry. So that's kind of the story behind Quantinuum. Thanks.
Hi, I'm Daisy. I graduated from CU in 2009. And I was in the group of a couple of professors here that have a joint research group, Margaret Mernon and Henry Kapteyn. And they focus a lot of their research around high harmonic generation and applications of extreme ultraviolet from high harmonic generation. And while I was in grad school, I heard some similar things to my experiences on the panel here. I didn't think I would stay in Colorado. By the time I graduated, I didn't want to leave. I realized at some point that I did not want to go into an academic career. And what I really loved was building stuff and fixing things and being like the best laser jock in the group. And by the time I finished up, there was somebody at KM Labs. So K is, it's Kapteyn Mernon Laboratories, was founded back in the 90s. And their CTO at the time was one of Margaret and Henry's original grad students from 20 years earlier. And he was always coming around to help us fix the lasers and stuff, and he became a real mentor to me during grad school, taught me a whole bunch, and basically said, you know, if you're finishing up, I want you to come work with me. So I couldn't pass up that opportunity. That was originally a research position, but then there was a point a little further out where I was watching the other things happening at the company. I was working on R&D programs, but also getting pulled into like the high-end custom laser systems that were getting shipped to help get those working and shipped out. And at some point, the production manager position came open, and I went, I could do that better than the last guy. So I switched to that, did that for a couple of years. I've been very fortunate at this little company to have a whole bunch of different responsibilities and job titles in the time I've been there, and that's one of the things I've loved most about working there, is I got trusted to do things that I wasn't necessarily qualified for, but could figure out. And so I, after manufacturing, ran service for several years. And then actually I overlapped with Chris Wood down there at the other end. He was there, what, 2, 3, 4 years, something like that. Taught me a bunch about engineering, how to take a systems engineering approach to product development. So I've been able to participate in that since then. I've done some sales. And then, yeah, it's been a whole series of things. So our flagship product these days is the harmonic generation source. So this is a box you can put on the table and put a femtosecond laser pulse into and convert your 800 nanometer light or 1 micron light into short pulses of extreme ultraviolet light at 30 or 13 nanometers. And we're really starting to get a lot of traction and interest from the edges of the semiconductor industry now. So there's a big installation that we did just about 2 years ago now at EMEC in Belgium. And this is a company that does development work for the semiconductor industry. And they're using our system to study the chemical processes that happen in the photoresists that they want to use for EUV lithography for next generation computer chips. And their phase 2 part of that program is really just coming online now, and they're starting to get interference lithography images, which is very exciting. And we're super proud of that. And I should let next guy go.
Hello, my name is Chris Myatt. I am a graduate in '97 in atomic and molecular and optical physics, atomic physics essentially, and I did my work with Carl Wyman, postdoc with Dave Wineland at NIST, which is right down the street. So I've been in Boulder basically for over 30 years now. It's a great place, and it's an amazing department given the quality of teachers and advisors that I've had. My background is, you know, I went to SMU in Texas, came up here for graduate school, and since then I have gone on. I worked for about a year and realized I really wasn't very good as an employee and started my own company, built that up, sold it. We spun out another technology as part of it, and now it is a medical diagnostics company that I'm helping to run. I was the CEO for for 20 years, and finally turned the reins over to a longtime lieutenant as we got to over 100 people, and it's just a big operation. And he gets all the headaches, and I get all the fun. I'm back in the lab. So that's my story. I'll stick to it.
Thank you very much. We want to have a sort of a Q&A session, and we're making a recording of this panel for the benefit of the people who couldn't make it to Boulder today. And so I'm going to ask that people ask their question into the microphone so that it makes it to the recording, and then maybe we can pass this one around on the panel. And so I have the microphone, so I'm going to ask the first question. And the first question is the following. You know, I'm the director of grad studies in the department, so I talk to a lot of grad students about different things that are going on in their sort of trajectory through grad school. And something that happens, not uncommonly, is that students encounter some roadblock along the path that they thought they wanted to go on, and they view this as a real tragedy. And I don't see it as a tragedy. I see all of our career paths through grad school and beyond as being a sort of a series of zigs and zags. And, you know, I have my office and I have my desk, and students come in and they think that, you know, from the age of 10, I was on this direct line to that desk. And it really just doesn't work that way. And so what I want to ask the panel is, you know, you've already talked about this a little bit, but are there times in your sort of trajectory where, you know, maybe some door closed and you took just some different path, or you took a little unexpected zig or zag in your career that might be useful for people embarking on, in grad school?
A good one. Is this on? Yeah. Okay, so I remember, I think this was my first year of grad school, sitting up, I don't know, maybe 10th floor of Duane Physics Tower, Friday night, massive quantum mechanics homework set in front of me, and I was on maybe the second problem. And at this point, I had come from the University of Wyoming, did really well there, and thought I was a super smart guy. And so I was all about theoretical quantum stuff. I was going to be a theoretical physicist. And so here I am, first year, doing okay in quantum, but all of a sudden I hear this racket next door in the office next to me. And the other two guys in my office, we go around the corner and look, what the hell's going on? And there's this whole office full of people drinking beer. And we said, what are you doing? You know, it's like they were already done with their homework set. They finished it in an hour. And I was on the first problem. And that's when I knew I was not in theoretical physics. It didn't dissuade me from physics and atomic physics and everything, but and I was always good at the experimental stuff anyway. But that was I don't know if it's a life-changing moment, but it was enlightening.
Chime in on that one, or should we take the next question? What do you think?
This was not. All right. You gave me the experimental trick, you know, see if I really have my chops still. Anyways, you know, I'd say a life-changing decision, which was, you know, I went to grad school thinking I wanted to teach. I enjoy teaching. I enjoy working through things, tutored a lot before going to grad school, et cetera. Really enjoyed being a TA and figured that was my route. But I got well into postdoc, and I remember one of the guys, you know, there were several postdocs together, and they were talking about, I think it was like one of these panels, and like, why do you like being a physicist? And someone said, well, you know, you get through this great experiment, this big problem, and you solve it, and you get to write a paper. And it dawned on me, God, I fucking hate writing. And that was actually the impetus for me to, you know, not go for an academic career, which I think was an option, but it was something where I said, you know, look, I just like building stuff. I like, you know, cool new solutions, figuring it out, building it, and making it work, and that's what I really want to spend. Now, I've learned that you ultimately have to write a ton as you go through your career, and I'm not that bad at it, I just dislike it.
Can I add to that? Yeah.
Yes, please.
Yeah, so that sparked some thoughts in me. I had a similar, yeah, there came a point where I was kind of like Chris's, where I'm like, oh, I'm not going to make it, I'm not going to be a professor. I'm very stubborn, so I stayed through and finished grad school, but knew I was looking for something else. And I love teaching and I love writing. And so, that was a little bit sad for me going into the research at the company. But like I said, I looked for other paths within the company to do other things. And probably the job where I learned the most was running service. And in both production and service, I've gotten to write, user manuals and troubleshooting manuals for our products. And then the best part of the service stuff ends up being teaching. We get these calls from somebody who says, hey, I've got this TS kit that my advisor said, get it working. That was the original KM Labs product. It was a TISAF laser kit that they started selling in the 90s. And so, if you could spare a few minutes to help one of those grad students and talk them through a few things and teach them stuff, I actually got to get some of that teaching back in the service world, and it's super satisfying.
You must have been really good because that laser was really not working that well.
I know, I remember, I'm sorry.
So, does anybody have a question? First one to raise your hand gets the microphone.
Hi, so I want to ask, how easy is it to do research in industry compared to like doing research in academia or like doing regular stuff in the industry? And like, also, how, let me check my note, sorry. A follow-up is like, how is doing research different from, like in industry, different from doing research in academia? And that's it. Thank you.
So I'd say it's easier in a lot of ways and it's harder in a lot of ways. For my research project, in grad school, I basically had zero money. Now there's so much money. So anything that we need to do things quickly and efficiently, we can buy, and it's just really refreshing not to have to like kludge things together and make things work. Another, even though that can be kind of fun sometimes, but we also have, at my company, we have a lot of support. So we have specialized divisions, like we have a whole optics division. So even though I actually really love like aligning lasers and stuff, there are other people who do it better than me that will do it faster. So I can always call one of them in and help me out with that. The way that I would say it's harder is because there's so much more focus. You have a product that you're trying to make. You can't be as exploratory in the things that you're doing, even though I think at my company there definitely is a lot of room for that, but less than you would have in academia. So in that way, it might be a little harder.
When I started my company, it was the exact opposite. I was used to having lots of resources at places like Jilla and NIST, and then it was literally in my garage, and we were dumpster diving outside of NIST to find old oscilloscopes and spectrum analyzers, and then repairing broken old oscilloscopes and spectrum analyzers. That was fun for us. It was sort of where we were at in our headspace. It is not for everybody. In terms of what it's like in general, so starting your own company is its own thing, and there's a whole slew of ways of doing that. Bootstrap, funding, that's a whole separate talk. But if you're going to work for a company, it's very company specific. Some companies have very strong R&D wings, other companies less so. In general, of course, it's more applied. You're not solving sort of the basic science. I mean, some very large companies maybe you're doing that, but by and large not. You're doing things that are leading towards products, and so I find that very rewarding because you develop a technology, you turn it into a product, now this product enables all these amazing devices and these amazing research. I think of it as a force multiplier. It's like, hey, your work is now amazing thousands of, cool data or cool research papers out there. But that's, it depends on what you want to do for yourself. And it is very, very company specific. Some companies, I know people who have worked who are research minded, are very frustrated at those. But then other folks, at other companies, they're incredibly happy. So, talk to the folks at the company. You just thinking of grad school. You don't, yeah.
And I guess I have a third example. CPI, it's a small company, it's a science company, so half of the folks at CPI are writing grant proposals, just like academics, probably more than we want to, sometimes. It takes, we're putting in a lot of grant proposals, writing papers. I'm the editor of the Space Weather Journal, so I really stay involved in the academic side as well as the product development side. But then there's the benefit that what the rest of the company is doing can also support your work, just like you're talking about product development. It's CPI, we've got a strong government services wing. And they bring in contract money, which then can support internal research and development that you're not going after NSF, NASA, DOE kind of grants for. So CPI may be a little unusual that we are a small business, science focused, and 90% of us have PhDs in the company. I do a lot of research myself, and I love the chance to still do that and build products at the same time.
Sorry, I saw your hand first, and then I'll come back to you next.
I notice you're all AMO. Could you speak to the?
No.
Oh, sorry.
I'm the weirdo.
I noticed most of you are AMO.
A quantum. That's what we just learned.
Right, quantum. Could you speak to that? Is that really representative of? I'm really sorry. But could you speak to why that is?
Yeah, I'm not.
I think it began as optical, really. There were various optical companies in Boulder, especially optical coatings was really one of the foundational technologies in the Boulder Valley here. Things like ion beam sputtering goes back all the way to Chris Myatt in my early days, and he's done a ton of this. And that sort of built upon, then the telecom bubble came along, and all of a sudden optical coatings became optical components. And pretty soon Boulder had a whole optical components community. And right about that time is when the Nobel Prizes started happening, and all of a sudden we have a laser community showing up. And you combine that with all of those things together with NOAA and NIST, and you've got systems, and you've got LIDAR. And then the other thing that Boulder had that's not even here anymore, along the diagonal, IBM used to have this huge facility doing hard disk drives. So hard disk drives was a major industry in the Boulder area, and there's probably 5 different hard disk drive companies that were founded in Boulder or the area. And so that flourished and created this micro components industry, but then it became the optical drive industry, and so there's a bunch of optical companies. So I think it's taken 20 years to get there and grew up as optics, and it's really more recently that the A and the M came back to it, if that makes any sense. But it began life optically, really, and because Boulder's had strong optics for a long, long time.
I'm not sure why it's so AMO heavy. I mean, Jill is freaking awesome, and so a lot of cool stuff spins out of that, and they're AMO centric. But in the industry base, and where a lot of PhD physics go in the area, aerospace is a huge employment base, and so we've got Lockheed Martin has a giant facility, Ball Aerospace has a very large facility, and a lot of that has nothing to do with AMO. And so there's also, there's a slew of startup companies that have nothing to do with AMO. There was, I'm not sure. I don't know. Maybe it's who the invitee knows.
I mean, I will say, I don't think the CU physics department looks like the PhDs you see represented here. It's not, like 90% AMO physicists at CU, but it is overrepresented compared to like maybe most physics departments in the United States because of JILA. And, that's a collaboration between CU and NIST that has been incredibly fruitful, and it's a really, I think, slightly different model for academia than a lot of physics departments have in terms of there being a lot more collaboration between professors, and just kind of the attitude that professors interact with each other with is a little bit, more community-minded and less competitive, I think. Certainly competitive with people outside the institution, but I think that also has had a pretty big impact on it being a place where talented professors want to come. also just Boulder is a really nice place to attract people to. But I mean, yeah, I mean, so I mean, even though CU does have a lot going on that's not AMO, it is true that the atomic physics is very well represented in the department, for what it's worth.
I just wanted to add, just a little bit of a sort of a mea culpa, which is that several of you hit on this, that the panel here is sort of representative of who we called and who responded to us first, and but I would say that the world of industry around this area and the world of industry that our PhDs go into is not quite like this sort of layout, not whatever, 6/7 AMO. It is more spread out than that, but it's more of a function of what we did in assembling this first panel for this first time. It's a really good question.
Yeah, so I'm mostly interested in theory, condensed matter theory more specifically. And I know that you guys are all having experimental background, so I was wondering if, are there industry positions available for people with a theoretical background? And if so, what should I do to kind of make myself more marketable for industry positions?
I mean, put something up on GitHub. I felt like, I mean, I'm not a theorist, but one thing I think that a lot of people who are concerned about jobs have probably noticed is that PhDs have a little bit of a PR problem. Like, I found my PhD to be very valuable in doing my job as an engineer, but sometimes I find myself having to sell the idea of a PhD to people in job interviews, and it's hard. And I think if you have something like a GitHub account with some cool projects in it or whatever, I mean, like, it can really help to just like have something technical to talk about to make it easier to discuss yourself. Because it's not that the PhD is not useful, but sometimes, in a job interview you do encounter someone you have to explain a PhD to a little bit, and it can be really helpful to have that kind of stuff, out there on the internet too. Although, I mean, all the kids these days have 600 little Python repositories, right?
Yeah, I think I would second that a little bit. And yeah, the way I've seen that theorists make good transitions into industry is by selling themselves as programmers and proving they've really done stuff. And yeah, I've run into the same thing with at interviews when I was graduating, some skepticism around the PhD, and now I carry that same skepticism when I interview people. But when I was at a couple of different places, they got very excited when they heard that I had handled a budget and a schedule. There was something that my advisors, my last couple of years of grad school, let me have a lot of the hands-on autonomy over ordering all the stuff to build a big laser system from scratch and get that all done, including talking to the vendors and negotiating some prices on things. And when I told the people at this startup I was interviewing at that, they got really excited about that. And so, I'm trying to think how that applies to theory, but to the extent that you can get to where you have more and more authority over the schedule of what you're working on and can sell it as something that you created and mapped out and planned and executed on, that's, I think, the way to show people that. But yeah, when I interview people now, we advertise for positions and get, PhDs applying for things that, one, they're overqualified for, and then, I really have to sort through them in the interviews and get a sense of, do these people understand actually what deadlines are and how to stick to a budget? And not everybody does.
So one thing I would say, I think everybody on this panel who is in industry does exactly 0% of what was their key effort in grad school. I did Bose-Einstein condensation. I do nothing to do with quantum statistical mechanics today. I know Chris Wood did cesium parity experiment. I don't think you're doing parity of anything right now these days. So one of the things is that on the flip side, earlier today I was explaining how to wind coils, electromagnetic coils, to some of our engineers who, engineers are supposed to be, the practical ones. I'm like, no, this is how you do it. This is the way you do it right. And so I use the techniques I learned in, 5.5 years at grad school, 2.5 years at postdoc, all the time, both on an organizational standpoint, on a technical standpoint, on a way to think through problems. That is the strength that you bring. Now, it's a very good comment that many theorists do wind up in something, that has computer or programming related. There are other outlets and so forth, but the things you learn, the disciplines you learn, how to think through problems will come back to you over and over. Sorry, I think you had.
Well, I think I'm going to be the weird one again and give kind of a counterexample. And I can't speak to condensed matter, but in the aerospace or in the space physics realm, which is where I am, I think it's a little bit different. Like I said, CPI's got 90% PhDs. We have 2 theoretical mathematicians on staff. They don't touch computers. We don't let them do that because they'd break our production products. And you give me 5 minutes, I could probably think of 10 space physics type companies in the Boulder area who are very similar, that are small to medium-sized companies that are really doing science, and supporting the national labs and supporting just fundamental research and doing NSF and NASA grants and really making a go of it that way. I mean, I think it is a viable option in industry. I guess I have one other thing I'm going to disagree on. I am actually doing exactly what I did in grad school. I studied magnetospheric particle dynamics, and now I'm saving the power grids from solar flares, so that's actually pretty related. It's pretty close. I might be weird. Yeah, I might be.
There are lots of theory jobs. It's not uncommon. Another company, a local company, is called TechX. They do high energy theory. It's all they do. And they just hire PhD physicists in theory. So there are jobs out there for you. And then I will say that we don't have, on our staff, we don't have any pure PhD theorists, but the PhDs we do hire, we expect them to be able to do modeling and do theory and know their way around that kind of stuff. So, and then, to your point, yeah, I'm not really doing too much of what I did, but the toolkit I'm absolutely using. And every now and then a molecular spectroscopy question comes up, and I am there. It does come up, actually. It's not, a couple times a year at least. Yeah.
There's also pretty good overlap of what I did in grad school to what I do now. Yep. But I just wanted to give another example of like a company that Quantinuum does hire a lot of theorists, like pure AMO theorists. Before we spun off, we had a theory division and a fair amount of theorists that didn't do a lot of coding. And then the company that we merged with, Cambridge Quantum, was just theorists, and they're so theoretical they'll even hire mathematicians, right? So I think there's definitely a place for people like that.
Thank you. Are there any other questions, or who has the next question? Okay, great. I'm going to ask one. So my question is, either in your company or in your knowledge of other companies in the area of this general type, how many, what do you think the balance is between doing things like applying to major institutions for grants, which is kind of similar to what faculty at universities or research institutions do, versus, making a little gizmo that, goes into your hand or goes really into the consumer space. I'm not being articulate about this, but I think you get my drift. So, yeah, please.
Yeah, I have thoughts on that. So at our company, we're about roughly a third funded by the government R&D programs. So there's the Small Business Innovation Research Initiative and Small Business Tech Transfer grants. And so that's pretty similar to academics. You write a grant proposal, you get it funded, you work through the stuff, turn in a report, get a phase 2 on that, and that really is crucial in funding the development of the laser and harmonic systems that we work on. And then about 2/3 of our, varies year to year, about 2/3 of our revenue is commercial revenue from products that we sell and ship to companies all over the world, about half US, about half overseas. I'm going to say ours are mostly not a little gizmo you hold in your hand. They're a big tabletop laser system that ships in, 7 crates, and then we send out a couple engineers to a customer site to install them for a week. And, they range from, they mostly cost, about as much as a house and take 9 months or something to build. But to be able to do a project like that and finish it and ship it out the door is what has really, I find one of the most satisfying things working at a company like this. And I like that I'm still next door to cubes in people who are working on the grants and will have me proofread a proposal or have me come look at their laser problem so I can get a break from, sales and looking at financial projections and all that good stuff.
There's a metaphor how I think about companies. I actually learned it from Dave Walba, who's a chemist here at CU. He started a company called Display Tech, which was actually not AMO. They had one of the very first high-definition displays on the market. He told me, and I took this to heart, I think about a company as a 3-legged stool, where one of the legs is R&D engineering, that's creating the new products. Another leg is sales and marketing, that's creating need for it. And then the third leg is manufacturing. We very much break down like that. In terms of our PhDs on staff, out of 41 people, we've got, I think, 6 staff scientists. Then in the production, we've got a bunch of folks that just have high school degrees. And then we've got a whole bunch of what we call research engineers. Those are folks with undergrad or master's degrees. I like the mix. I like the folks talking to one another, and I think that's very fruitful. It is, it varies a lot by companies, but.
I think it also varies a lot within companies, honestly. So like at my company, we were kind of founded by a bunch of people who worked for a Department of Energy lab and basically had a really cool idea to build something and couldn't handle getting through the bureaucracy to actually build it, and just kind of spun off a company to build it instead. DOE labs are particularly notorious for their bureaucracy out of all of the labs, I would say. But so there's a very academic orientation to the people at my company, and there are some of them who really want to spend all their time writing proposals and writing papers and writing application notes and kind of having these kind of like big, very academic sort of ideas. And then I think I'm a more detail-oriented person. I'm the one who was bothered that like a control on the front panel of a product was charged up to 600 volts. I was like, we can't really sell that, can we? like I would be the one who would be like, what are you talking? So like I think that like then I ended up in more of an engineering role and also more of a management role because of that orientation. And I think that when you have a team that works well together, people who are interested in different things end up doing different things, and that's okay. That especially at a small company, roles tend to be very dynamic and fluid in that way. Less so at a big company. At a big company, you have a pretty well-defined role, typically.
Well, thank you very much. Apologies, I'm starting to get a little distracted because the food smells really good. So I think we're at about that time where I'd like to wrap up this part of the panel discussion. And if you wouldn't mind, let's give them a hand because I really appreciate them coming.